This video is on chapter 10, atmospheric circulation and weather systems. So in the previous chapter, we have read about how temperature is distributed over the surface of Earth. We have also seen that not every place on Earth has the same temperature and what are the causes behind it. Then we have also read about what causes low pressure and high pressure system. Then how winds move from one place to another, what happens when warm air interacts with cool air, and how heat and moisture is distributed across the planet, which helps in maintaining the Earth's temperature. So we have read about all these stuffs in the previous chapter. Now this chapter on the other hand deals with a little advanced version of the previous one, wherein we may encounter some technical aspects of wind pattern, weather system, and atmospheric circulation. So overall it will be an insightful chapter with a slight bend towards technical aspects of some natural phenomena. Alright then, let's begin with the first topic, atmospheric pressure. So let me first tell you the meaning of the word atmospheric pressure with an illustration. It is the pressure exerted by the weight of the atmosphere, and atmosphere consists of gases, water vapor, dust particles, etc. So in simple terms, the atmosphere that surrounds the planet Earth, it exerts some pressure on the Earth. Now the question would be, why does the atmosphere exerts pressure? Well, you see, we all know that everything around us is made up of tiny particles called molecules, right? Even our own body is made up of tiny molecules that we cannot see. And in a solid object, these molecules are tightly packed and closely bound to each other. That's how it maintains the solid shape. Whereas in a liquid, it is a little more free. You know, the molecules are not very tightly packed. And in the case of gas, it moves around freely like anything. They are not bound to each other at all. They are free to move here and there. Now in an atmosphere, there are a lot of gases, right? So the gas molecules move around freely, and while moving here and there, they often bump into objects like one molecule with another, then rocks, trees, then our bodies. Now these molecules, when they hit all these objects, it creates a pressure, and this pressure is not happening from just one direction. It's in omnidirectional, meaning that it is not only exerted from above, but also from down, from side, from every direction at once. Okay, so this is what is atmospheric pressure. And always remember, pressure decreases with height or altitude. And we also know that as we go higher, temperature also decreases. That means we can also say that as the temperature decreases, the pressure also decreases. Now an easy way to understand this is you take a utensil, you put water in it, and you start boiling it. And it takes 100 degrees Celsius to boil the water. The moment the temperature is 100 degrees Celsius, you will see water molecules will start moving rapidly. And it is because of the increase in temperature this thing is happening. That means increase in temperature leads to rapid movement of molecules. And if the temperature is low, then there will be hardly any movement. I hope now you understand how atmospheric pressure works. Just to reinforce these 2 points before we go to the next topic, what we have seen is that with height, pressure decreases, and we have also seen that temperature, if it increases or decreases, pressure also increases and decreases, directly proportional. Just remember these points, okay? Alright, now let's get to know about vertical variation of pressure. So when we hear this term vertical variation of pressure, with the word vertical in it, you can easily figure out that we are talking about the variation of pressure while going up. As you can see, it's written over here that in the lower atmosphere, the pressure decreases rapidly with height. When we talk about lower atmosphere, we are referring to the troposphere. I hope you remember that figure which shows the different layers of atmosphere as we go from inside to outside. And I also hope you remember that the length of troposphere is somewhere around 10 kilometers from the surface of Earth. And then if you remember, the top of the troposphere is quite cold, and that's why nearly all of the water vapor, clouds and dust particles in the atmosphere are found in the troposphere. And now when you look at this table 10.1, here you see that on the left side you have the column where it shows from sea level, that is the ground level. It goes up to 10 kilometer, that is the end of troposphere. And next to it is the column with pressure. And again next to it you see the column which represents temperature. And it clearly tells you that as the temperature increases, the pressure increases. When the temperature decreases, the pressure also decreases. After vertical variation of pressure, it's time to get to know about horizontal distribution of pressure. So by the word horizontal, you can figure out that it's talking about the sideways movement of air. Now we know that wind moves horizontally, and while they move horizontally, they have speed and they do exert pressure. And this is what is known as horizontal distribution of pressure. So to understand the horizontal distribution of pressure, we do that by drawing isobars. So isobars are basically lines connecting places having equal atmospheric pressure. Iso means equal and bar is the unit of measurement for pressure. And if you remember in the previous chapter, we read about isotherms. They are lines joining places having equal temperature. So remember these two terms, isotherms and isobars. And always remember this point. Isobars play a major role in determining the speed and direction of wind. So the way we read air pressure on a surface is by looking at the patterns of isobars. Whenever you see these circles and the corresponding number, for example, here it says 1014 MB low. That means it is the lowest pressure zone of that region, okay? And then you see 1020 MB high. That means this enclosed region is the region with high pressure zone. So in between these two regions, you can see the speed of wind and direction of wind. That is how the MB is increasing and decreasing depending on high pressure to low pressure, because air always moves from high pressure to low pressure system. So MB is the unit for measuring pressure. MB stands for millibar, and we measure pressure with the help of an instrument called barometer. Let's go to the next topic, world distribution of sea level pressure. So when you hear the word sea level, I'll just show it to you with an illustration. So sea level means the level of the sea surface. It is used in figuring out the height of geographical features such as hills and mountains, and it is used as a universal standard. So basically we use the sea level as a standard scale to determine the height of various physiographical structures. Now going forward, we are going to read about equatorial low, subtropical high and subpolar low. So these are all high pressure and low pressure belts that are located on the Earth's surface at various latitudes. Now instead of covering these topics in this video, I've made a separate video on it. I'll put the link of that video in the description. Just go there and check it out, because this topic needs a nice elaborate video. That's the reason I made a separate video on it. So I'll link it in the description. Just go and check it out. Alright, let's move on to the next topic. Forces affecting the velocity and direction of wind. We all know that air moves in two directions, that is vertical and horizontal. The vertical movement is due to warming of air, which is called convection, and the horizontal movement is due to the differences of atmospheric pressure. Now let's quickly summarize the forces that are responsible for the horizontal movement of wind. The first one is pressure gradient force, which is the force that moves wind from high pressure to low pressure zone. Now gradient means slope, so the pressure gradient is strong where the isobars are close to each other, and it is weak where the isobars are apart. The second one is frictional force, which means the closer the wind is to the Earth's surface, gravity will have tremendous influence on the speed of the wind. That's why the wind in the upper atmosphere, that is 2 to 3 kilometers above the surface, are free from frictional effect, and winds over the oceans have minimal friction. The third one is Coriolis force. I've covered this topic in the video which moments back I told you to watch it in a separate link. So again, go there and refer to it. I have explained there very nicely. So in a nutshell, it is the force generated due to rotation of Earth in its own axis. We know that Earth rotates from west to east. Always remember that winds don't travel in straight lines. The actual path of wind is in circular motion. And we also know that winds blow from high pressure zone to low pressure zone. It is the Coriolis effect that makes the winds move in circular motion. Always remember this point. Wind in low pressure zone rotate anti-clockwise in the northern hemisphere and clockwise in the southern hemisphere. Similarly, winds in high pressure zone rotate clockwise in northern hemisphere and anti-clockwise in southern hemisphere. At the equator, the forces cancel out each other. That's why the direction of rotation changes between the two hemispheres. Please don't forget to watch the video. I put the link of the video in the description as well as on the top right corner as a ticker. Please do check it out. Now we will get to know about the general circulation of the atmosphere. Before I explain the general circulation of the atmosphere, here are some of the important factors that influences atmospheric circulation. You will notice that some of these factors are the same that we went through in the previous topic. Alright, the first one is latitudinal variation of atmospheric heating. So what does it mean? As we go away from the equator towards the poles, temperature drops. And we know that. And that has a lot to do with the creation of warm air and cool air, which in turn has a greater influence on wind's movement. The second one is emergence of pressure belts. By pressure belts, we mean low pressure and high pressure belts. So you see these high pressure and low pressure zones are strategically located on the Earth's surface. It goes something like this. At the equator, it's warm, so we have low pressure. After that, in the subtropical region, we have high pressure, which is called subtropical highs. And then as we go near to the subpolar region, there we have low pressure belt. And finally in the polar region, it's high pressure. So like this, we have the pressure belts that are positioned strategically all over the Earth's surface, which plays an important role in the movement of wind. The third one is migration of belts following apparent path of the sun. Now pressure belts, that is the high pressure and low pressure zones, they change with the position of Earth while revolving around the sun. For example, during the month of January, it is winter in the northern hemisphere. At this time, many regions in the northern hemisphere witnesses high pressure zone. Likewise, in the month of July, when it is summer in the northern hemisphere, low pressure zone builds up in many places. So you see these pressure belts migrate with Earth's position. And while facing the sun and when pressure belts migrate, it does affect wind's movement. After all, sun is the ultimate source of energy. The fourth one is distribution of continents and oceans. So oceans play a fundamental role in shaping the climate zone that we see on land. Even areas hundreds of miles away from the coastline are still largely influenced by the global ocean system. Land is opaque and absorbs sunlight and gets heated up very quickly compared to the oceans. On the other hand, ocean is translucent. Therefore, it takes time to heat, but water loses heat slowly compared to land. Now, if you look at the tropical region, that is the water around the equator, there the ocean gets heated massively, and from there the heat is distributed all around the globe, both in the form of evaporation, that is when warm air goes up in the atmosphere and moves towards the pole. That's how water vapor humidity builds up in the atmosphere, and also the fact that warm ocean currents move towards the nearby land masses, thereby affecting the regional temperature and weather pattern. The fifth one is rotation of Earth. Now, rotation of Earth should immediately remind you of Coriolis force. As we have read about this, and I've also asked you to watch a separate video on it, so please I urge you to watch that video. The link is there in the description. Now this topic in the box revolves around this term called ENSO, E-N-S-O. If you break it, EN stands for El Nino and SO stands for Southern Oscillation. Because ENSO phenomena mostly occurs at the southern hemisphere, just right below the equator. And when you look at the term oscillation, it gives us a hint that something oscillates from one place to another or back and forth. If you want, you can pause the video and think about what could be that thing. Well, it's the temperature that we are talking about. And not just any temperature, ocean temperature. It is the ocean temperature that oscillates back and forth from warm temperature to cold temperature and vice versa. Now the next question that should be in your mind is, which ocean are we talking about? I'll give you a hint. It's the largest one, Pacific Ocean. You see, Pacific Ocean is this large pool of water that exists on the western side of the American continent and eastern side of the Asian and Australian continent. This large pool of water gets intensely warm due to the fact that it exists right at the equator, and we all know that the equatorial region receives great amount of sun rays all throughout the year. So far we have learned what and where ENSO takes place. Now it's time to know how it all happens. To understand how ENSO occurs, we will need to break it into 3 phases. That's how it will make sense, and step by step the concept will get clearer. The first phase is neutral phase. Actually, there is no such thing as a neutral phase when it comes to any of nature's phenomena. You see, nature has a constant ongoing cycle that has never stopped. But for our own understanding, we will have to create a neutral state where we can see how a particular thing starts and goes on. So the first phase among the 3 phases is the neutral phase. In this phase, the central Pacific Ocean is warm. Now let's bring in the trade winds. Trade winds are these winds that blows in the tropical region from eastern side to the western side. They are also known as tropical easterlies. So as we know that the equator receives great amount of sun rays, and that's what warms the Pacific Ocean. The trade winds pushes the warm ocean current towards the Asian side, because trade winds blow from east to west, and that makes the western Pacific Ocean warm. You know the region around New Zealand, Australia and Indonesia. This region is called the Western Pacific Pool. Here the ocean temperature is warm. The warm ocean current affects the surrounding atmosphere by increasing the temperature as well as the moisture content. And we know that warm air rises high into the atmosphere It is through the convection process, and that's how clouds are formed, and then it rains. The warm air then travels east towards Eastern Pacific Ocean. You know, the region near South America, especially countries like Ecuador and Peru. The warmer air, when it goes up, it reaches the end of troposphere. And if you know, the top of the troposphere is cold. When warm air meets cool air, slowly it loses its moisture content and the air becomes dry. The dry air travels towards the Eastern Pacific side and comes down over the Peruvian coastal region, making the region cold. This pattern of rising air in the west and falling in the east continues, and it is known as Walker circulation. So this was the neutral phase. I hope you understood this cycle. It's plain and simple. Now comes the second phase. It's called El Nino. So in the neutral phase, we saw that the trade winds played an important role in pushing the warm ocean current towards the Western Pacific. Now in this phase, the trade winds are weak. Yes, there are few months in a year when the trade winds are weak. When the trade winds are weak, the warm ocean current do not get any kind of push. So what happens is, the warm pool of ocean water at the Western Pacific slowly moves towards the central and eastern side of the Pacific Ocean. So this is where the oscillation term comes in. You see, the warm ocean current is replacing the cold ocean current that exists in the central and eastern Pacific. When I say replace, what I mean is that the cold water is dense and it settles down in deep ocean, and warm water goes up and takes over the surface of the ocean. Okay, I hope you're understanding. When this warm ocean current moves, everything that is associated with it, like the convection process, then the formation of rain cloud, everything moves along with this warm ocean current. What you will notice now is that the Walker circulation that we saw in the neutral phase, that one big looping pattern, it's now breaking into two parts. Just look at this loop. As a result, the ocean temperature near Australia is cool and there is no rain, though the inland parts of Australia witnesses severe drought condition. But on the other hand, near the Peruvian coast, the warm pool of ocean current brings heavy rain, flood to the American continent. So whenever you hear the word El Nino, immediately think of warm ocean current. And the third phase is La Nina. This is similar to the neutral phase. In this phase, the trade winds are strong. Since trade winds blow from east to west, hence it pushes the warm ocean current from the Eastern Pacific towards the Western Pacific. Now imagine this. Cold water is dense and it settles down in deep ocean. So that means the temperature of the ocean surface is warm. Now if the trade wind pushes the warm surface ocean current towards the Western Pacific, the cold water from the deep ocean immediately comes up at the surface. There's a word given to it. It's called thermocline. Thermocline is the rising path of water temperature. And the rest of the process is same. We saw that in the neutral phase. Western Pacific region of Australia, Indonesia, New Zealand gets heavy rain storm. The effect of La Nina is more on these countries than El Nino. So El Nino is a warm ocean current and La Nina is a cold ocean current. Remember that. If El Nino is at the Eastern Pacific, then La Nina will be at the opposite region, that is Western Pacific, and it oscillates back and forth. Now we will get to know about different kinds of winds. The first one is seasonal winds. These are the winds that come during a particular season. As you can see, there's a word season attached to it. They are different from local winds. Seasonal winds are much stronger. I'll give you an example of a seasonal wind. In India, the seasonal wind blows from the southwestern region right after the summer season. We call that as incoming of monsoon. Then in the month of November and December, there's another set of seasonal wind blowing from the northeast. We call that as retreating monsoon. You know, it brings rain in the region of northeast and Tamil Nadu. So these two are an example of seasonal winds. I believe you can easily figure out as to what is the reason behind their origination. You see, we witness different seasons due to the revolution of Earth around the Sun. Sun rays also oscillates between the northern and southern hemisphere. When it is winter in northern hemisphere, the southern hemisphere witnesses summer. So you see, there's a shifting of region of maximum heating. You know, some places receive more heat compared to other. And that leads to the formation of low pressure and high pressure system. And we clearly know that the winds move because of the formation of high and low pressure belts. This is how seasonal winds originate. The next one is local winds. Now, these are the wind that you feel every single day when you go out. Now the question is, how do local winds originate? Well, they originate due to regional temperature differences. Now these winds are not very strong and they are not big in scale compared to seasonal winds or trade winds. As I said that local winds originate due to regional temperature differences. Suppose there is a place which is warm, then naturally the environment of the air in that region will be warm. Now warm air rises and cold air sinks because it's dense. You can also notice this in your house. You switch on the AC and if you don't close your door, the cold air will go out of the room because it is attracted towards the warm air. When there is such a movement of air, that's how local winds originate. Let's go to the next one. This one is land and sea breezes. Now we all know that land and sea both absorbs and transfer heat at a different rate. Now what I mean by that is, imagine a hot sunny day. The land will heat up faster than the sea. Now if the land heats up faster, obviously that will make the surrounding air warm. And warm air rises, and that's how low pressure zone is created. And if you look at the sea, the temperature is cool when compared to the land. And that gives rise to high pressure zone over the sea. Now we know that air moves from high pressure to low pressure zone. That's how during daytime, wind blows from sea to land. And we call it as sea breeze. Now at night, everything changes. Land loses heat faster and is cooler than the sea. Now land which is cool, it has high pressure zone and the sea has low pressure zone. And we know air moves from high pressure to low pressure. So at night, the wind blows from land to sea and we call it as land breeze. And one thing that you will have to remember is that both land and sea breeze are winds that blow at the surface level. The next one is mountain and valley winds. First of all, these two winds are related. They both occur on a daily cycle, one after another. That's the reason they both are related. Another thing is that both mountain and valley winds are local winds. They are not global winds that travel long distances. Now, this is a mountain and it has a slope, and a valley is this. Now, during daytime, the surface as well as the slope of the mountain heats quicker than the valley floor. The heat of the mountain will heat the air higher up in the atmosphere at a much faster rate. And we know that a warm air expands, which will create a small low pressure system at the mountain top. Now the air at the valley floor is cool, which creates a high pressure zone. And we know that wind moves from high pressure to low pressure zone. So what happens is that the warm low pressure zone at the top as well as at the slope of a mountain attracts cool air of the valley floor. So what you will notice is that the wind or the air blows upward along the slope of mountain. There's another name given to this kind of wind. It's called anabatic winds. Similarly, at night, the reverse condition takes place. The top surface of the mountain loses heat faster than the valley floor. As a result, the cold air at the top of the mountain flows down along the mountain slope. Because cool air is dense and it sinks. That's how the wind goes down slope towards the valley floor. Now these winds are called katabatic winds. And if you see, it is a wind that carries high density air from higher elevation down a slope under the force of gravity. If you have to remember the word katabatic, the word katabatic sounds cold, right? Something which is solid, rigid, like an ice. Always remember katabatic winds are cold winds that comes down from a higher elevation to a lower portion of land. On the other hand, anabatic wind is the opposite of katabatic. Now, katabatic wind mostly occurs in Greenland, Antarctica and Alaska, whereas anabatic wind can be found on any mountainous region that heats up sufficiently due to sun rays. This is how mountain and valley winds originate. Now we will read about air masses. First of all, let's understand the meaning of the word air mass. By air mass, we are talking about the weight of the air. So to find the weight of the air, we will have to consider what all exists in the air. For example, we know there is water vapor, moisture in the air. And we also know that air is both warm as well as cold based on the surrounding temperature. Therefore, we can say that an air mass is a volume of air defined by its temperature and water vapor content. Now, as I said that wherever the air flows, it acquires the characteristics of that area. If the region is warm, then the air will become warm. Similarly, if the region is cold, then the air will be dry and cold. Now, based on this fact, there are 5 major source regions for the formation of air masses. I'll show you all these regions on a world map. The first one is warm tropical and subtropical oceans, these regions. Then we have subtropical hot deserts over here. The next one is cold high latitude ocean. The next one is extreme cold snow covered continents in high latitude. So all these places. And the last one is permanently ice covered continents, which are the polar regions of Arctic Circle and Antarctica. So these are the 5 major source regions for the formation of air masses. Now based on these regions, there are 6 types of air masses: maritime Arctic, maritime polar, maritime tropical, and continental Arctic, continental polar, and continental tropical. Wherever you see the word maritime, that means the air mass forms over the ocean. Maritime is associated with water, remember that. Likewise, wherever you see the word continental, it's landmass. Now let's read about fronts. When 2 different air masses meet, there's a boundary between them. It is called a front. In other words, it's a transition zone between cold and warm air masses. Let's say a cold region develops cold air mass and it moves towards a warmer region with warm air mass. And let's say it replaces it, then it is known as a cold front. Likewise, if a warm air replaces cold air, then it is known as a warm front. Now there is a third front, which is called stationary front. In this situation, the boundary of both the air masses does not move. Now you must be wondering, what kind of a situation is this and what kind of a weather condition will it create? Have you ever witnessed a weather condition during daytime? It's cloudy and the feeling is that it may or may not rain. We all love that weather. It's not sunny nor it's rainy. The temperature is not too warm, not too cold. So those are the moments of stationary front, when the boundaries of warm air mass and the cool air mass do not move. There is also a 4th type of front. It is called as occluded front. This one is fairly easy to understand. We know that warm air rises and it creates a low pressure zone. Now when the warm air rises from the surface, immediately cold air rushes in to take over the place. When all of this is happening, there will be a point where the boundaries of cold and warm air meets. That point is called as occluded front. This is also the point where turbulence occurs, and it is generally associated with stormy weather. So occluded fronts are dangerous points. Now there are 3 topics left, which are extratropical cyclones, tropical cyclones, and thunderstorms and tornadoes. I'll cover these topics in a separate video because believe me, it requires a separate video of its own because the concepts are a little technical, and as it is, this chapter is getting too long and we have already covered so many aspects of weather, and I think now you can easily figure out that why weather patterns, atmospheric circulation, these are all complex topics in general, and I don't want you to get confused about it. So I'll cover them in a separate video and put the link in the description. Meanwhile, I hope that you have found this video helpful, and I also hope that it has cleared a lot of your doubts about atmospheric circulation and weather systems. The question answer of this chapter can be found on the website. The link is there in the description. And that's it. Thank you for watching, and I'll see you in the next one.